So one structural task you can do that's a little more detailed is to construct a histogram of a graph. And you saw this in the elastic MapReduce assignment if you completed it. So we saw that the out degree of a vertex is just the number of outgrowing edges. So some notation, let's say for each integer d, we'll let n of d be the number of vertices with that out degree d. Okay, so for example, in this graph, we have, what is the out degree of this vertex? It's 0. There are no outgoing edges. The out degree of this vertex is 2. There are 2 outgoing edges. The out degree of this vertex is 4. There are 4 outgoing edges. So now we can count them up. We can say, how many vertices in this graph have out degree 0? Well, there's just one. It's this one. How many vertices in this graph have out degree 1? Well, there are 3 of them. This one, and this one, and so on. And then you just plot d versus n of d and create this histogram. So we see 1 vertex at 0, 3 at 1, 2 at 2, and so on. Okay. So why might this be a good idea to do? Well, it tells us something about the graph we're looking at. So if we see this kind of a pattern, so we might see this kind of a pattern where very many vertices in the graph have a very small out degree, and fewer as you go out the x-axis. Or potentially you could see this other pattern where very few have a small out degree and many more have a high out degree. So this is a much more connected graph, right? Everybody tends to be connected to everybody else in this case. Most people have a very high out degree. Most vertices have a very high out degree. And here very few have a very high out degree. Okay. And it could be sort of more mixed, like this. It could be sort of bimodal. So what's going on here? Well, if we see this pattern, then you can model this as an exponential distribution where d is in the actual exponent. And what this tells you is that it becomes very unlikely, the further you go out the x-axis, it becomes exponentially less likely to find a vertex that has that out degree, right? So most have a small out degree, one or a few, and as you go further out, it's much less likely. Okay, and so you can see this effect very clearly if you plot it with on a log scale. It becomes linear on a log scale. Now, the thing about this distribution is a random graph has this distribution. So what do I mean by a random graph? Well, this is take a set of vertices and then choose 2 vertices at random and connect them with an edge. Then choose another 2 vertices completely at random and connect them with an edge, and so on. If you follow that process, you'll get this kind of a distribution of the connectivity, right? There'll be it's very unlikely to construct a vertex that is connected to lots and lots of other vertices using this process. Okay. So fine. So it turns out that you don't find random graphs in nature very often. Okay. That's unfortunate because if you did have a random graph, it's actually fairly easy to work with. And by work with, I mean implement some of the tasks that we'll be talking about, say, in parallel, because you can split the edges up across a bunch of different machines and just work with them all sort of independently. But what you see more often in practice are these power law distributions, the zip distribution, where there's some x that's in the exponent. You're raising the degree d to that exponent. And human-generated data tends to have this distribution. And if you think about it, there's at least one way to get to build some intuition for why these come about. Okay. So instead of choosing 2 vertices at random and connecting with an edge, instead, when you choose a vertex to connect with an edge, favor those ones that are already well connected. Okay. So why would you bother, or why would this happen sort of naturally? Well, think about it. If you're in a social network and you have someone who joins Facebook for the first time, are they more likely to connect themselves to someone who's already very popular, or are they more likely to connect themselves to a bunch of people who don't already have lots of friends? Well, it's much more likely to connect yourself to someone who's already very popular. That might be who introduced you to Facebook in the first place. Or with Twitter, are you more likely to follow people that already have a lot of followers, or more likely to follow people that do not have a lot of followers? Well, more likely you're going to connect to and follow, you join Twitter in order to follow popular people. Okay. You can also think about this in terms of maybe the internet or the web. When you create a web page and put it on the web, are you more likely to link to sites that already have a lot of links or not? Okay. And the answer is you're more likely to connect to, it's reasonable to say that you're more likely to connect to web pages that already have a lot of links. Okay. So with this preferential attachment model of constructing graphs, you'll generate this Zipf-ian power law distribution. These are the distributions you tend to find in nature or on the web, whether you call that nature or not. And they have a distribution like this. They have this fatter tail, this long tail. So now it's not quite so unlikely to find vertices that have a very, very, very high out degree. Okay. And you can see this effect more clearly on a log-log scale plot where both axes are on a log scale. I think I'm not a huge fan of using log-log scale except very sparingly because lots of distributions end up looking linear on a log-log scale, but these are defined to be linear on a log-log scale. So you can do this kind of structural analysis. You can construct this histogram of very large graphs like the web, which Broder et al. Did in 2000, and we're probably overdue for another analysis of this type, but it's become computationally pretty difficult to produce these kinds of plots for the current internet. Okay, so here's the plot, here's the histogram of the web, and the question is this an exponential or is this a Zipf-ian power law distribution? And you can see it's kind of here in the description, but it's pretty clearly a power law. This is a log scale axis, and this is a log scale axis, and this looks pretty linear. So what the authors went on to do, which I think is pretty interesting, is produce this kind of schematic of the overall structure of the web. And this circle in the middle here is a big, strongly connected component, meaning that the pages within that component, if you can reach X from Y, you can reach Y from X for any two pages. Okay, but then there's also an in and an out set of vertices, pages, that are kind of about the same size as the strongly connected component. So these are things that are, you can reach the strongly connected component from these, but you cannot reach back from the strongly connected component. So they link into the main mass of the internet. Okay, and then similarly on the outside, there are things that link from the strongly connected component, but you can't get back. And it's about these big 3/3. And then they pointed out that there are indeed tubes that connect the in to the out directly, not going through the strongly connected component. And there are these tendrils that sort of go off nowhere, but these are perhaps minor components relative to the main three. And then you also have these sort of disconnected components that are smaller. But this is sort of interesting to understand the basic, physiology of the internet, and it's, again, difficult to produce this now.